Hello, welcome to a video about specific heat capacity. Specific heat capacity is a measure of the quantity of heat that must be added or removed to change the temperature of an object. Energy can be added to or removed from a system without causing a change of state. The energy that is added or removed causes a change in temperature. The change in temperature depends on the mass of the object, the amount of heat transferred to or from an object, and the nature of the material, so its specific heat capacity. These variables are linked through the formula Q equals mc by change in T. So that's heat equals mass times specific heat capacity multiplied by the change in temperature. In Stage 1 physics, you'll need to be able to describe and explain specific heat capacity. You'll also need to be able to solve problems using this formula. The state of matter can change when heat is added or removed. For example, you can think about the changing states of water. So when water transitions from ice to liquid to steam, so heat is being added progressively to result in these transitions. Energy can be added or removed without a substance changing state, but adding or removing energy will result in a proportional change in temperature. Specific heat capacity, which is represented with C and is measured in joules per kilo per Celsius, is a measure of the quantity of heat that must be added or removed to change the temperature of 1 kilo of the substance by 1 degree Celsius or 1 degree Kelvin, because Celsius and Kelvin use the same scale. So over here we've got a table of some specific heat capacities. Water, ice and steam all have different specific heat capacity. So that means it takes a different amount of heat to be added or removed from these versions or states of water to change the temperature of water in these given states. A lower specific heat capacity means that it takes less heat to be added or removed in order to change an object's or a substance's temperature. So a quantity of heat is represented using a capital Q, and it's added or removed to change the temperature of a mass m. And this is all related using this formula here. So the quantity of heat is measured in joules, mass is measured in kilos, specific heat capacity is measured in joules per kilogram per Celsius, and change in temperature is measured in degrees Celsius. So in order to work out the quantity of heat added, you just need to multiply the mass by the specific heat capacity by the change in temperature. For example, you might be asked to calculate the quantity of heat that is added to raise the temperature of a 2.5 kilo mass of lead by 25 degrees, given that the specific heat capacity of lead is 127 joules per kilo per Celsius or per degree Celsius. To do this, you just use that beautiful formula that was on the previous slide. So change in heat is equal to mass multiplied by the specific heat capacity multiplied by the change in temperature. Our mass is 2.5 kilos. I'm just going to make that look a bit more like a C. Our specific heat capacity is 127 joules per kilo per degree Celsius, and our change in temperature is 25 degrees because that's how much we're increasing the mass of lead by. So subbing it all in, 2.5 kilos multiplied by 127 joules per kilo per Celsius by 25 degrees Celsius. Popping all of that into your calculator will give you 7,937.5 joules. So that's the amount of heat that needs to be added to the 2.5 kilo mass of lead in order to increase its temperature by 25 degrees. As another example, the temperature of bath water decreases by 28 degrees when 22 megajoules of heat is removed. The specific heat capacity of liquid water is 4,180 joules per kilo per degree Celsius. Determine the mass of water in the bath. So this is asking for the mass, and it's giving you the change in temperature, it's giving you the amount of heat that is removed, and it's letting you know the specific heat capacity of water. So you still use the exact same rule, but this time you're going to have to rearrange it in order to find what you're looking for, which is the mass. So rearranging to make mass the subject, you will be dividing the heat by the specific heat capacity and the change in temperature. Our heat is 22 megajoules, which is equal to 22 by 10 to the 6 joules. Your specific heat capacity is 4,180 joules per kilo per degree Celsius, and change in temp is 28 degrees Celsius. Popping all of that into your equation, you'll get 22 by 10 to the 6 joules of heat on top, and then 4,180 joules per kilo per Celsius and 28 degrees on the bottom. Popping all of this into a calculator will give you 188 kilos. So there's 188 kilos of water in the bath. Just to recap, heat is a transfer of thermal energy from a hotter body to a colder one via contact, so via conduction. Thermal energy flows until it reaches thermal equilibrium, or the objects reach thermal equilibrium, and that means that when the temperature difference is zero between the objects, so they have the same temperature. So to summarize, to reach equilibrium temperature, heat is transferred from objects with a higher temperature to objects with a lower temperature, and this occurs until thermal equilibrium is reached. What this is saying here is that the heat that flows out of object A is going to be equal to the heat flowing into object B. So just say that object A, whatever it is hotter than object B. If they're in contact, then the heat is going to flow from object A to object B. Any heat that object A loses, object B will gain. Therefore, the heat that is leaving object A is going to be equal to the heat that object B is gaining. This here is exactly the same. It's just written in the Q equals MC change in temperature format. And this can be used to solve problems, for example, looking for the equilibrium temperature after this thermal equilibrium has been reached between two objects. So for example, you're cooling some water by adding ice cubes. You add 150 grams of ice, and the original temperature of this ice, that should be minus 12 degrees. I'll just add that in now. So you're adding 150 grams of minus 12 degree ice to a 250 ml glass of water, and that glass of water is currently at 25 degrees Celsius. The specific heat capacity of ice is 2,100 joules per kilo per degree Celsius, but for liquid water it's 4,180 joules per kilo per degree Celsius. And you need to calculate the equilibrium temperature of the water. In order to do that, we'll say that the heat that leaves the water is equal to the heat that the ice gains. Therefore, the mass of water multiplied by the specific heat capacity of water multiplied by the change of temperature in the water is going to be equal to the mass of the ice multiplied by the specific heat capacity of the ice multiplied by the change in temperature of the ice. Therefore, 0 is equal to mass of water specific heat capacity of water, change in temperature of water, plus mass of ice, specific heat capacity of ice, change in temperature of ice. For the changes in temperatures, we can say that this is equal to the equilibrium temperature minus, which will be the final temperature of both the water and the ice, minus the initial temperature of both. I'm going to put IN for initial, just because I've already put a lowercase I for ice. So this will mean that 0 is equal to the mass of water multiplied by the specific heat capacity of water multiplied by the equilibrium temperature minus the initial temperature of water plus mass of ice, specific heat capacity of ice multiplied by the equilibrium temperature, which will be the same as water as it is for the ice, minus the initial temperature of the ice. I'm now going to expand all of this out, and then I'm going to factorize it, and then we'll be able to get these t's by themselves, so we'll be able to work out what the equilibrium temperature of the water and ice is. So now what I'm going to do is collect this and this, and then I'll be able to factorize. So that will end up being T multiplied by mass of water, specific heat capacity of water, plus mass of the ice, specific heat capacity of the ice. And then we're just left with these leftover terms. So that will be equal to minus and then mass of water, specific heat capacity of water, and then the initial temperature of the water, plus mass of the ice, specific heat capacity of the ice, and then initial temperature of the ice. I'm going to move on to another slide just to fill this out, just because the writing's a bit big on the iPad, and then from there we'll be able to get to the equilibrium temperature of the water, which is what the question asks. So from here, if I want to get T by itself, what I'll do is I'll bring this term onto the other side of the equal sign, so I'm just adding that whole thing to both sides, and then I'm going to divide by these brackets here. So this will look like T being equal to mass of water, specific heat capacity of water, and then initial temperature of water, plus mass of ice, specific heat capacity of ice, and the initial temperature of the ice, divided by the mass of the water, the specific heat capacity of water, plus the mass of the ice and specific heat capacity of the ice. The mass of our water is going to be 0.250, so 250 ml is equal to 250 grams for water. And then the specific heat capacity is 4180, and then the original temperature is 25 degrees. And then we're adding the mass of ice, which is 0.150, specific heat capacity is 2100, and then the original temperature is minus 12 degrees. Then we divide all of that by the mass of water multiplied by the specific heat capacity of water, plus the mass of ice multiplied by the specific heat capacity of ice. Popping all of that lovely big sum into your calculator, you'll end up with an answer of 16.4. So that means that the equilibrium temperature of the ice when it's added to water, or the overall mixture of the ice and water, is 16.4 degrees Celsius. So that's the temperature that that mixture ends up being when it reaches equilibrium temperature.